On today's lecture, we are auditory, the center. Cubesat missions, that's what we're going to talk about today. We're going to talk about Cubesat missions. Without a mission, as you know, there ain't no point in making a Cubesat. Cubesat's got to have a mission. The mission's the most important thing. The mission determines our hardware, determines our software, determines the type of orbit that we want, determines all the other controllers and sensors that are necessary for the Cubesat. All right, so you can see here's a bunch of little sensors, bunch of little Cubesat sensors. All right, so clearly this is part of the design, hardware, and coding of the Cubesat. So one type of mission is the proof of concept. And the proof of concept mission is not scientific. It's more engineering. You're not trying to study the magnetic field or anything like this. You're just trying to see if your new technology works. So Austin had this idea where we were talking about using the heat of the sun instead of as solar power with solar cells. Instead, what happens if we use a Stirling engine, or in this case, a thermoelectric generator, right? So this would be a proof of concept where you're actually trying to see, will this technology work in space? Can this become a viable technology for CubeSats? And you can see here's a little thermoelectric generator. The thing is tiny. You can see like it's soldered right there. You see how tiny this thermoelectric generator is, right? So there's been some work done here where they're saying that the gradient isn't big enough for it to be effective as a legitimate source. But my argument is, okay, but how did you design your thermoelectric generator? I mean, if the poles are this thin and the walls are this close, well, then the gradient might be small, okay? So I'm not suggesting we throw the idea of a thermoelectric generator out the window. It could just be a design issue. How could it be designed in a way such that the energy difference between the two walls is maximized?
Let's make our entire CubeSat a thermoelectric power generator.
Right. So here they have this hot plate, right? Where I think the idea that Austin was getting at was actually have the wall of the CubeSat actually is the hot side, So we would have to look into the physics of this to really be able to evaluate that. Now, on one hand, we have to say, yeah, but there's all these engineers out there, and they're 10 times smarter than we are, and they're engineers. Okay, well, that's true, but that doesn't stop the fact that maybe you have a brilliant idea that they haven't thought of. A lot of times, people that aren't in the field actually have the more ingenious ideas, because a lot of times people in the field can't see the forest because of all the trees, right? They get into this way of thinking that limits them from seeing the big picture, right? Because they get what's called a rut, like back in the old days, wagons had wheels and the roads were dirt, and so ruts would form in the road that the wheels would go in, and you couldn't get out of them. So it was almost like being stuck on a railroad. So it's called being in a rut, because you're just stuck going straight ahead, and you don't have any new ideas. And so it's not an unusual phenomenon where a person comes in from outside the field, has a brilliant idea, and then everyone in the field gets mad because they didn't think of it, right? So you have to keep that in mind, that we could take a look at this. Another proof of concept is the solar sail. Solar sail it's interesting that the angle is important. It's how you angle it, because if you want the thrust a certain way, you have to align the solar sail a certain way. The pressure is very weak. 0.0035 pounds of force per square mile. I don't know if that's per minute or per whatever. But you know, it's really, the solar wind is really, really weak. So I mean, you can be on the moon walking around, and the solar wind, you're not even going to notice it. But the reason why it's effective is because it's integral. So that force is constantly being applied. So you can, even though it's weak, you continually speed up. See what I mean?
Yeah.
Yes.
Yeah, you see what I mean, right? So it's like when we do calculus, I'll teach you how you integrate a force. So at any moment it's weak, but if it's continual, then it's going to always be adding and speeding you up. Okay? And I'm showing this because Austin had mentioned some type of solar sail. Yeah, Austin had also mentioned an idea about tethers. Believe it or not, there were some missions that did proof of concept on tethers. So the MAST program was a tether experiment, launched 2007, to see if tethers were survivable in space. All right, it didn't work that great. Apparently there was something, so they got some information there. Japan lost tethered autonomous robotic satellite. The satellite was named Kukai. And
Wait, guys, we need a cool acronym for our satellite.
yeah. So apparently it had a tether. I don't know what the tether did, but it had a tether. Tempo 3 by the Mars Society. Tethered experiment. Okay, and so is meant to demonstrate artificial gravity. I don't know if this has happened yet, but I know that's something that we've mentioned too as a cool proof of concept. All right.
So that means our proof of concept of using tethers as a form of nutation control is still open.
Right. Yeah. The Al Globus model, right? Here is University of Michigan, and they did one where they had a solar array unfold like an accordion. Well, that proof of concept worked, and so now it's a normal thing, right? But somebody had to be the first person to do it. That's a proof of concept. Lithium ion capacitor. Okay, probably not considered a big deal, but somebody had to be the first to do it. Okay, so this is proof of concept. It's all engineering. Let's see what else we got. Oh, of course, this one, the magnetorquers. When we did that lecture on Polysat CP3, the mission was to see if magnetorquers would work. And magnetorquers are really cool because what they do is they say, okay, here's the Earth's magnetic field. I'm going to adjust the magnetic field so that I can maintain orientation. But I'm super cool because I have no moving parts. I'm like a MacBook. I have no moving parts, no fan or nothing. And so it just probably, I imagine it just creates some kind of a opposite magnetic field to, readjust so that it always has the same orientation towards the Earth. All right, so proof of concept. What else we got? Oh, okay. So leaving proof of concept behind, you can also use CubeSats for art. For example, shooting stars. Okay, so we had this Japanese satellite, and it was going to create artwork by dropping shooting stars into the atmosphere.
That would have been so cool.
Doesn't
So
seem like it worked.
didn't work. It got delayed.
What would it shoot out? Like debris?
It shoots out these little pellets, and you can see how the pellets are different colors.
Mm-hmm.
And then as the pellets enter the atmosphere and burn up, they create shooting stars.
Oh, they burn up. Okay, I was gonna say, like, what happens if the pellets are just stuck there?
Well, and what the lady liked about this, because this was a woman's idea, what she liked about this is that you could see the shooting stars from multiple cities. So you were basically putting on a light show that people in different cities could watch. And so that's imagine that, right? That's pretty amazing. Anyway, so they were testing it, and they found out basically that one of the parts got stuck. And you would think, okay, can we just unstick that part? But apparently satellite construction is complicated, and they would have to do a whole rebuild on it. So I think it's getting pushed back a couple years. So they says now we have to wait until 2023. So that's a long wait, unfortunately. Yeah, but this is kind of unusual that, you know, a satellite for artwork. Now, for me, I wouldn't have it so complex. I would just have the thing rip open and all the little pellets just go.
Well, Mr. Herman, think about it. You could draw pictures in the sky. You can write down Austin is the best.
Herman, it would literally just be a one-time use if you did that, because then it would just be like.
Imagine if it like something happened where it's instead of spelling Austin is the best, it just like completely misspelled it.
Yeah,
Let's
that's
do
true. Well, imagine if it did shoot them all out at once.
That'd look amazing.
No, people would think it was the end of the world. There'd be all these being tracing over the atmosphere. All right, so that is the art satellite. Getting into the nitty gritty, the measurements. So I guess we would just call this like the raw science kind of thing. So we know like a lot of them have measured temperature, like you see here.
Oh no, it's in Kelvin.
Hmm.
That's like 200. Okay, so that's like plus or minus 703 degrees, right?
Yeah, I
It's
think
Celsius.
that's pretty close.
Wait,
I don't like Kelvin. Why do they make us learn Kelvin?
We
Wait,
don't even know Kelvin. Well, who
wait,
is
0 Kelvin. That's the
Absolute
maximum.
zero.
That's absolute zero. But Kelvin works on the same multiplier as Celsius.
Yeah.
Just
so
that 0 is in a different spot.
Yeah, so basically it's just offset by 273 degrees.
Yeah.
So about 280 Kelvin is about 7 degrees Celsius.
Still easier than Fahrenheit.
Well, anyway, so in his book, Sandy Antunes recommends looking at all the different sensors on Wikipedia. And here's a list of all the sensors on Wikipedia. There are lots of them. Now, obviously, breathalyzer is not something you're going to put.
Alcohol meter? There's an alcohol meter?
Don't you want to find out? Don't you want to find out if space is made of alcohol?
Yeah, what if we never figure that out?
No, clapometer, right? So if you do the shooting star satellite, you can add a clapometer to see how many people on Earth are clapping when it happens.
The creep meter.
Yeah.
Sending a CubeSat with an alcohol thing to different planets.
And then we got some more over here.
A protractor? Yeah, we're just gonna put that up in space.
I'm gonna stick a little plastic rinky dink
Yeah.
protractor in space.
Hey,
It's
don't
gonna
judge.
get melted by the sun.
Oh, a parking meter? Or for all those pesky aliens who park.
Can we bring a measuring spoon into space, please?
Hmm.
No, you have to use a parking meter so that we can tax all the aliens that park on the moon. We need to use the parking meter so that we can tax Elon Musk's car.
Yeah. Our the
Yeah.
new mission statement for our CubeSat is to make contact with aliens and find them immediately when we find them.
Right. Find like the first lunar lander and put a parking meter next to it, and then charge the government millions of
That's
dollars.
how we raise money for the CubeSat.
That'll be our second CubeSat mission right there. Done.
Space Club will never be broke.
Or just find Elon Musk.
Yeah, find the car that you shot up into space and tax
Taco
it.
meter.
Spirometer, just lung capacity in space.
Quartz crystal microbalance? Why would you need to measure the thickness of a thin film?
Thymometer, fermentation.
A tachometer so that we can know the rate of blood flow of the CubeSat.
You got to think it through. You guys got to think this through.
Or a spirometer so that we can know the lung capacity.
There's a zymometer again, fermentation. Again, that theme is coming up. All right,
And then there's
so
just a weighing scale.
A ruler.
Mr. Herman, how heavy do you think the CubeSat will be in space?
we could put a weighing scale in space, but I think everything's gonna weigh 0.
Mr. Herman, that's genius, Mr. Herman. Think of it like this.
Yeah.
So our CubeSat has to be 1 kilogram, right?
Mm-hmm.
They don't mention where it has to be 1 kilogram. In space, that 1 kilogram you can fit so much in space and fill it up to 1 kilogram.
They
You
didn't
make your own gravity to make 1 kilogram.
Yeah.
We have found a loophole.
Well, if you make a big enough CubeSat, it's gonna get its own gravitational well.
Exactly,
get
and
one
that's
G.
when we get a 1 kilogram reading. It's because of the weight
Yeah.
of the own scale.
Yeah, we just have to build a big enough CubeSat that it bends space-time until we get 1G.
Hey, but you
So
know how
basically the Death Star.
expensive materials are? How are you gonna build such a huge thing?
I don't know, turn the moon
It's
into it.
gonna cost so much money.
We can build it out of Play-Doh.
No, let's
Save
build
on
it out of
money.
build it out of Mars.
But the only way to know would be to weigh it, though. No.
Well, the thing is, if you think about it, Michaela, we can just build we can have a very small electrical suite, right? But we can just build the rest of the planet, the little asteroid, out of Play-Doh to save on costs.
Play-Doh is expensive. It's like
Okay.
25 cents for a tiny cup.
How about Legos? Because we all know that Legos stuck together are basically indestructible.
Yeah,
Yeah.
but they're also crazy expensive.
But they're light.
Yeah, they are light.
They're
So
So
hollow.
we can make an even bigger planet.
Why would you spend that much money to be ridiculous?
Because Death Star.
Launch a Lego Death Star.
Okay, we can also send a wind vane up there. Probably one that looks like a rooster. Those are very popular.
Or a ruler. Just a standard school ruler.
Like Pharaoh made Joseph a ruler. Okay.
Oh,
Haha.
Okay. Biology. So, in December 2006, they launched a CubeSat, and the purpose of this CubeSat was to perform experiments with E. coli bacteria. It was not cheap by CubeSat standards. It cost $6 million. The goal was to measure magnetic change from being exposed to the space environment. So you can imagine how hard that would be. Like, what kind of sensors? I mean, because one of the reasons why they're okay with biological stuff is because no matter what happens, no matter what mutations happen, it's all going to burn up on re-entry. So
Unless
we get a heat-resistant super virus.
Oh yeah, one of those.
right. So, but besides those, it's all gonna it should burn up on re-entry. So there's no danger to mutant E. coli destroying the world. You know. But I mean, what
you're just gonna
kind
be
of
pooping
sensors?
all
I
the
mean, you're
time.
sending them into a radiation atmosphere. What
It-
kind of sensors? How are you measuring to see what the environment is doing to little tiny bacteria?
With $6 million worth of sensors.
Yeah,
Microscope.
whatever they're doing,
Just
it's got to be
little
pretty
microscope.
amazing.
I mean, with $6 million, they could at least get an electron microscope.
Maybe that's what they're doing, you know, because you're not gonna look DNA. Cinema collaboration between UC Berkeley and Hong Kong and Korea and Puerto Rico monitors space weather using magnometers and particle detectors. Okay. And anyway, so with these more scientific ones, you're basically matching the sensor to whatever it is you want to measure, right? So, and by the way, the word sensor and detector are used pretty much interchangeably. So if you wanted to call it a detector, you can. If you want to call it a sensor, you can.
I don't think I want to call a ruler a detector.
Yeah. Right. So anyway, so this is kind of like this type of mission is you just decide what you're going to measure. Okay. So I think we've got that. All right. And finally, there's the imaging mission where you're using some kind of a telescope. And there's probably a gray area between a camera and a detector, depending on what wavelength you're trying to analyze. I mean, in a sense, anything that you're imaging is a camera, right? So you can see here you've got X-ray cameras, ultraviolet, visible light, infrared, millimeter, radio waves, right? They're all cameras, but they're all measuring different wavelengths. And the result is that you get all different images, right? So the X-rays are probably from like the cyclotrons in the middle of the black hole, surrounding the black hole, where visible light you're getting, you know, almost all mass, right? Radio waves you're getting, I think more dusty particles because, or maybe not. I'm not an expert on this. You know, I mean, we know radio waves can travel through more stuff than short wavelengths.
Yeah, that's why you see less with the X-rays.
Right, right. Where radio waves can travel through, they can't travel through mountains, but they can travel through
Buildings.
Buildings, because they're so wide. So here's again, it shows galaxies in different wavelengths. Radio waves is showing cool gas. Ultraviolet is showing hot stars. Visible showing most stars. Infrared showing dust for some reason.
Infrared's the prettiest one.
Yeah, infrared is very attractive. X-rays, hot gas. That's kind of interesting. That I don't know if it's be limited to black holes. I'm not sure if that's, but you know, just a high energy cyclotron type of energy. Here's the sun in different wavelengths, infrared. So in infrared, you can see the temperature difference more clearly with the sunspots, because the sunspots are coming up and they're cooling, so they come across as darker. Okay, optical, don't see a whole lot there. Ultraviolet, you know, X-rays, you can see the corona much more clearly with the X-ray telescope. Here's the sun again at different wavelengths. So it's a unit of angstroms, but angstrom is like it's still it's essentially still wavelength, right? So you can see that looking at the same picture of the sun in these different wavelengths, you can see all different kinds of features. Okay, so again, you want the right detector for whatever you want to study. When you're studying the Earth, it's called remote sensing, and there's a lot of data that we can get that's already been done. So remote sensing is a fairly popular mission objective, because obviously if you're in low Earth orbit, you might have a better time imaging the Earth than you would space. I imagine if you're on the dark side of the Earth, you would get an incredible view of the stars. That might justify that. But you know, what kind of telescope can you put on a tiny little CubeSat? Probably not a very big one. Okay, and so in terms of resolution, you know, remote sensing the Earth probably going to give you the best results. All right, so that's all these missions are doing. They're checking out the Earth, you know, and probably doing it. I mean, think about the camera on your phone, right? You've got, like, on your iPhone, you've got these tiny little cameras, but they're high definition, right? So you can have a small high definition camera, and if you do this, though, you need to make sure you have attitude control so that you can aim it at what you want to study. You don't want your camera to be rolling all over the place if you have a mission objective, right? And so this has been done, obviously. One of the most interesting things was there was a CubeSat with a camera on it, and lo and behold, they discovered that lightning storms give off gamma rays, and that was never known before. So CubeSat actually made a unique scientific discovery that no one ever had predicted. Lightning actually gives off gamma rays. So yeah, so it's a viable science to use CubeSats for remote sensing. So if you're going to do that, if you're going to do remote sensing, then obviously your orbit makes a difference. If you're in this kind of almost circular low Earth orbit, you're basically limiting your view to the equator, right? And that might work for you, it might not work for you. For example, even if you're studying hurricanes, right, the equator is okay, but it's not perfect. If you're in a polar orbit, then you're going to get the entire Earth, because as you can see here, as the Earth rotates, you're getting a different slice of the Earth every time. So polar orbits are really, really good for getting the entire Earth. Okay, and this is, as you guys know, this is how they finally mapped the moon and discovered the water, is they did a polar orbit of the moon. All right, so a polar orbit makes a lot of sense if you want to map the whole Earth. Then of course there's the sun synchronous orbit, which is kind of new to us, but it gives the same angle towards the sun every time, and perhaps that would be useful. There are a few CubeSats that went with sun synchronous orbit. I don't know if they went with it on purpose or if it was just that that's the ride share that they got, but I think some of them intentionally wanted a sun synchronous orbit. So it's possible that you may come up with a mission concept where a sun synchronous orbit is ideal. Okay. So also, if you're examining the Earth, your attitude control needs to work so that you're camera is always oriented towards the Earth and not spinning out into deep space. Obviously, if you're doing remote sensing and your spacecraft has wobble or it's aiming the wrong way, pretty much blows the whole mission, right? Right, and so there has to be some kind of attitude control system to keep the camera aiming the right direction. So here's here's a couple reaction wheels and a magnetorquer combo. So the magnetorquers, the reaction wheels, the combination, keep it aimed the right way. And here's some other technology, little gas thrusters, little DC motors, little reaction wheels, everything to just kind of give it these little torques to reorient it.
You only need you only need 2 reaction wheels to keep the right angle that you want. Although one of them is gonna have to be going on overtime.
Yeah.
Yeah, you might be right about that.
But you probably also might want to have more than the bare minimum as redundant or safety.
Safety schmashy.
I think you do. I think they do say that reaction wheels do need something else to dampen them at times, because apparently this kind of off motion can build up, which is maybe that's why here we have a combination of reaction wheel and magnetorquer to kind of so that if this residual motion builds up, it gets a little pushback on it. I'm not describing the physics very well, but something that I bumped into looking at CubeSats. But it's still a minimalistic design, and that's what you want. You want to keep everything as simple as possible, right? That's like when we were talking about CubeSat failure, what they said was, don't get over your head. Keep everything designed as simple as possible. All right, and there's a little thruster right there. The little Wally thruster, we call it the Wally.
So what they're doing is they're actually hiding a flame
Fire extinguisher.
Yeah,
Yeah.
fire extinguisher.
Mm-hmm. Little fire extinguisher in there.
That's
Why
the Men
Okay.
in Black.
Why do you have that picture of me and Joe?
You kind of look like the Men in Black right there.
You gotta admit
Yep.
that was good. You gotta admit that was good.
Besides
I mean-
sunglasses.
That did more for my ego than
Wait, how did it help your ego?
because you two were following me around everywhere.
Oh
Anywhere I
yeah.
went.
We were supposed to guard Mr. Herman.
Yeah.
Because of any assassins, you know.
Was it my birthday or something?